Okay, thank you all for joining. I'm excited to present some data today that we've been collecting in partnership with Hamilton to do library prep with our NICS product. So my name is Casey. I'm an application scientist from DPX Technologies. And data I'm going to be presenting to you today is some library prep with both Pillar and Watchmaker library prep kits using our NICS product in replacing mag beads in the cleanup and size selection workflow. So I want to give you a brief overview of the technology first before we jump into some data. So our whole premise is that we put media inside of pipette tips to enable purification. So rather than using mag beads or resin, we put media, different types of sorbent into pipette tips to do the purification directly in the tip. So our NICS tip product is designed for nucleic acid purification, both for extraction from different biological matrices. So if you're interested in whole blood DNA extraction, we actually have a poster here for that as well. And also we do size selection, double-sided size selection, and PCR cleanup. So this is what I'm going to focus on today for library prep, and with the intent to generate samples for downstream sequencing and analysis. So really we wanted to kind of get a data set together to prove feasibility that we could use our NICS product for sequencing and library prep. So the workflow is really simple. The media, again, is immobilized within the pipette tip. So we add binding buffer to the sample. We aspirate up and down in the silica media to bind nucleic acid to the tip. And then we move to a wash solution and we aspirate and dispense in the tip to wash. And then we do the same thing to elute. So there are no beads involved and there's no magnets. And I know a lot of you are probably very familiar with bead-based workflows, so I'm not going to spend too much time on this, but a typical workflow would require adding your sample to beads and doing a mix. You have to pellet those beads on a magnet for a period of time, remove the supernatant from the bead pellet, and do one wash solution, remove that. Then you would do typically a second wash, another removal of ethanol very close to the well bottom to make sure that all the ethanol is removed so that you can dry, and then remove the plate from the magnet so that you can add elution buffer. You need to mix those beads vigorously to get the pellet back into solution so you get good recovery before going back to the magnet to pellet your beads, and then removing your eluate and collecting that in a new plate. This process typically takes 6 pipette tips and 12 deck positions if you're processing 96 samples. Our process, we add binding buffer with 1 tip to the sample. We mix that about 20 times to make sure it's homogeneous. And then we come in with our tip, our NICS tip, and we aspirate and dispense the sample to bind nucleic acid. Anywhere from about 5 to 30 cycles, depending on how much recovery you want. And then we move to a wash solution to wash the media. We dry actually by moving the plunger and the head and then picking up tips and blowing out an air gap to blow air through the media to dry it. So we do that 4 times. And then finally we elute the sample in your elution buffer of choice. So that could be water, low TE, or whatever you want to use. Comparing this to bead workflow, we just use the 2 pipette tips. So 1 standard tip and our NICS tip in that process. So in total, you're saving 4 tips. So for plastic, single-use plastic reduction, it's helpful there. And we also use fewer deck positions. So actually 5 fewer. So you can use a full carrier. Now you have deck space that you freed up on your instrument. So I have some representative data here just showing some of the performance of the tip. So we like to use DNA ladder as a control sample. It's really helpful for, we have a controlled amount of mass going into the cleanup so we can look at recovery, reproducibility, and also we can use it for our size selection. So we can determine, what binding ratios allow you to remove certain size fragments. So with this, we were using a 1 kb DNA ladder. So we expected to recover all of these fragments, and you can see at 30 binding cycles and taking about 30 minutes, we get about 85% recovery at room temperature. If you're not terribly concerned with maximum recovery, you can actually reduce the number of cycles. So you could do 5 or 10 and get your NICS cleanup workflow down to under 20 minutes, actually. It's notable if you are concerned with high recovery, you can also heat during that elution to really get maximal recovery. And we've shown we can get 95+% recovery under those conditions. So for size selection, so if you're familiar with doing this with beads, you would alter the bead ratio to your samples to size select out smaller fragments. So we did this for the whole genome sequencing using Watchmaker's kit, and I just wanted to show you some representative data. So here we used a 100 base pair ladder, you can see in red, and at a 0.5x ratio of binding buffer to sample, you can see that we've removed mostly 300 base pairs and below, maybe about 50% of 400 base pair fragment, and we retained everything 500 base pairs and above. So this was, I'll show you later some data we generated using Watchmaker's kit for whole genome sequencing and using size selection with our product as well. You can also do double-sided size selection if you're familiar with that too, but we would use 2 NICS tips to do that process. So the first data set I want to show you is actually working with Pillar Biosciences OncoReveal MPN panel. So this is a targeted amplicon sequencing panel looking at 6 amplicons, looking at pathogenic mutations implicated in blood cancers. Again, working closely with Hamilton, they have assay-ready workstation method on Starlet that we used, and we make contrived samples with control this myeloid mutation mix that has the mutations that are detected in the panel. And so that was positive sample 1. Positive sample 2 was a mix with human genomic DNA, so essentially like a 2-fold dilution. And then we used wild type genomic DNA. We did have a fully automated method on the Starlet, so we ran that method, and then we took, at the time we were doing the bead cleanups, we took a sample set off and ran those on the Vantage with NICS. So truly, as much as possible, trying to make this a side-by-side comparison with beads. And then we replaced the samples back on the instrument to do the index PCR and repeated that process. So as you can see, this is the expected size of the amplicon from the Pillar kit. So they're really, both beads and NICS, we generated amplicon of the expected size, and we were able to clean up any primer, dimers, anything like that. So we don't see any noise in the below 300 base pair. And actually what we saw in this experiment is we did get higher recovery and lower variability with NICS tips here. So this was exactly what we expected to see and what we wanted to see, and really comparing to beads, we might have performed a little bit better. And the output of the Pillar kit, and their bioinformatics is looking at the variant allele frequency in these specific genes for these mutations. So again, positive sample 1, we had the myeloid mutation mix, and positive sample 2 is about a 2-fold dilution. So that's reflected here in the variant allele frequency. And we did not detect any mutations in wild type genomic DNA or in our negative controls. So we didn't have any cross-contamination in the workflow. So again, here we're demonstrating feasibility, and that we're getting comparable results really to the beads. And we have a lot of data showing with PCR cleanup that the NICS product is working really well. We really just wanted to take this through with the library prep kit all the way through getting sequencing data and see how it performs. The next study that we did was using Watchmaker's DNA with fragmentation kit. So we wanted to do whole genome sequencing to demonstrate the size selection performance of NICS. So here we used, again, human genomic DNA, 100 nanogram input, and the fragmentation. Here was kind of a semi-automated process. So the bead cleanups and the NICS size selection, they were all done on automation. And one thing to note is kind of interesting that we had to alter the binding ratio with NICS compared to beads. So like what we found is that using a 1x ratio with NICS, we actually retained some of the smaller fragments. So we just had to tune that and lower that binding ratio to make sure that we remove the smaller fragments from our libraries. So actually the first round of sequencing that we did, we had some smaller fragments there, and we were able to come back and kind of rescue these samples by doing another 0.5x cleanup and removing those small fragments and sequencing again. And that's the data that I'm going to show you here. So we were aiming for right around 550, somewhere between 500 and 600 base pairs for our library size for whole genome sequencing for, Illumina paired end sequencing. So we used TapeStation to QC our libraries, and we were able to achieve both with beads and nicks. We were able to achieve that library size. And I wanted to show you the insert size distribution from our sequencing data. So again, you can kind of see here with beads, it looks like our size selection maybe retains some smaller fragments, where with nicks, our ratio biased a little bit more to the right, which is fine. And I think the takeaway really is that similar with beads, you can tune that ratio and you can really dial in the fragment size that you want. So, if we really wanted to try to replicate the same distribution, we could increase our nicks binding ratio and repeat this and get a little bit closer. But altogether, our goal was to just ensure, we could actually generate libraries and do size selection with our nicks product and generate quality sequencing data. So this is high level, but through doing the QC of our sequencing data, we're looking at all these different metrics, right? So we wanted to make sure that we weren't failing any of these QC checks with the sequencing data, and we performed as good or maybe a little bit better in some of these areas compared to beads. That's probably attributed to the difference in the library insert size. So I would say we have equivalent performance to beads here. So I know that's a lot of data to go through, and as I wrap up here, I welcome any more questions that you have. So as I was going through this process of evaluating beads versus nicks, these are kind of some notes really that I took, some benefits for nicks. So again, we're using 4 fewer tips per sample. So I know, we should all be trying to minimize single-use plastic if we can. So for this process, it actually has a potential to significantly reduce the amount of tips that are used. Yeah, I like this. So, there's no beads, of course, so we don't have any dead volume with beads. And our friends at Pillar coined the term bead text, which I like, so I added that here. But this truly can save you some cost. You don't have any dead volume. Our media is contained within the tip, and it's really a different concept altogether. A huge benefit is that we use fewer deck positions. So for one cleanup, we would use 5 fewer deck positions. A lot of library prep kits use at least 2 cleanups or maybe more. So you're really freeing up a lot of deck space on your instrument to do other things, or maybe to create more fully automated workflows with that. Our tips are, they're standard tips that we get from Hamilton. We repackage them with our media and sell them, and they're stored at room temperature. So you don't have to take your beads out of the fridge. You don't have to, wait for them to equilibrate. You don't have to resuspend anything. They're really handled like standard consumables, and they can stay on the instrument deck. One thing I really like about the tips is that you don't have to aspirate at the very bottom of the plate well to remove ethanol. You can just set your fixed height aspirations at 1 to 2 millimeters, and there's really no risk of pulling vacuum with the tip as you're trying to remove all the ethanol from your bead pellet. There's no risk of bead carryover because we do not use beads. You don't need a transport device. We're not moving any plates around. We're just using the pipette head to move to the different plate locations, and no magnets required. So for us, next steps really are, we want to kind of push the limits a little bit more. The experiments we did were kind of in the middle range of like sample input and, maybe not testing the boundaries of the technology. So some future direction that we want to go is to maybe test watchmaker's kit with a really low input sample volume or mass rather, to ensure that we can recover that small amount of nucleic acid and then go through the same whole genome sequencing workflow, and also do more reads, get more whole genome coverage, and kind of really push the boundaries there a little bit and make sure that we're performing equivalent or maybe better than beads. With Pillar, we tested, our lower sample set 2 was still probably about 4 to 5x above the limit of detection. So we want to repeat that and actually go down and see if we get to 1% or lower than in the variant low frequency, to really see if we will still compare to beads and detect those mutations at very low frequency. As I mentioned, we also, we can do extraction of DNA from different matrices. So we want to couple this with doing upstream DNA extraction as an input into library prep. So we're actively working on that here too. So I put this image of our dialogue here, and we have a great partnership with Hamilton, and we have Hamilton package files ready to go. So if any of you want to evaluate the technology, especially if you have Hamilton, we can provide that package file for you and support you with doing evaluation of the technology. We do offer tips that work with other liquid handlers as well. So we try to work with as many different technologies as we can and different applications. So if you don't have a Hamilton and you have other liquid handling platforms, we can likely come up with a solution for you as well, or we might already have a standard product for that. So I really want to thank all of our partners with Hamilton. Both Watchmaker and Pillar were very collaborative throughout this whole process, and I really appreciate their input on experimental design and data analysis. We used the Nevada Genomics Core facility for our sequencing, and they've been great, as well as my colleagues in our R&D lab, Paul and Leighton. Thank you.